Alrighty, guys. So today we are here for the Plant Podcast number 6. We're joined with us by a very special guest. We are so excited for this podcast. We're with Dr. Mike, and we've got Maddie, and I'm here just to absorb all this really, really cool information. And we're going to rip in and we're going to talk to you guys about all things energy production, how we consume fuel, how that fuel is then turned into working muscles, and then how we can better improve our performance through proper fueling, making sure we're hydrated. We might even talk a little bit about intra and extracellular hydration and things like that and fluids. So we can probably just have a really nice yarn about this for, as we were just saying, probably 50 hours, but we're going to condense it down a little bit, and hopefully you guys can take away some information. If you get one thing out of it, then that's a massive bonus. So maybe just to kick things off, maybe just give us a little introduction about what you do, what you study, what you major in, and what has kind of led you to this wealth of knowledge.
I am Dr. Mike Todorovic, Senior Lecturer of Anatomy and Physiology at Griffith University. My student cohort, a whole bunch of aspiring health professionals, nurses, doctors, physios, whoever it may be, and I love just talking about health communication, science communication, health communication, taking complex topics, simplifying it. My background is in neuroscience, so I did a PhD in clinical neuroscience, but was in education teaching throughout that time, and then sort of stuck into academia, and then my role at the university sort of split 50-50 between teaching and research. And so, just love talking about the human body. I say that I'm a jack of all trades, master of none, right? I know a little bit about a lot of stuff.
Well, this kind of goes hand in hand for what I do. I am not in academics at all, but I like to chuck my hand up for whatever sporting event might come up. So whether it's endurance or strength or I'll play table tennis if I have to, golf, it just, you name it, I'll chuck my hand up and have a crack. So that kind of goes hand in hand.
Yeah, and also as a naturopath, we tend to be more of a generalist as opposed to a specialist, because we need to know a little bit about anatomy and physiology to be able to work out how to prescribe and diagnose to a certain degree. But we also need to have enough of an understanding of how it interacts with the holistic system and the microbiome and the environment, and on a holistic level, our attitude towards life and everything as well. So when we talk about all this sort of stuff, it's really kind of cool. And what I really loved about having you on today is when someone's an expert or not, because they're capable of teaching. They're capable of explaining something that they know, or they know something well enough to be able to explain it so others can understand it. And I've been following all of your stuff on the social medias for years and years and years.
Oh, cool.
Yeah, and absolutely love it. And I actually recommend everyone to follow as well. So we'll make sure we tag everything in, because it's a brilliant resource. And not many people are out there just giving out resources like that. I mean, you're giving out the same snippets of the level of information that you'll be teaching the students.
Yeah, university level content.
Yeah.
And you're right about being able to teach, understanding and teaching. My students will always say to me, what's your biggest tip to best study for this content? And I say, go teach somebody what you've learned.
Yeah,
that's cool.
I go, I don't care if it's your dog or your grandmother or your partner or whatever. If you think you've just understood something, go tell it to them.
Yeah.
And you'll find out what you don't know and what you do know.
Yeah.
And that's it. And what you don't know, you go, I'll go back to the books and study that. You don't have to then study everything, just the things you don't know. So it is the best way. I mean, when I study for myself, when I'm doing research for myself, I always write it down and say it and do it in a way that as though I'm teaching somebody what I've just learned. That's how my YouTube videos started. It was simply just, because in a 12-month time period, I'll do, dozens of hours worth of face-to-face lectures for students, and then you put on repeat you do it again next year, and you don't remember everything. Like, it's just not the case. So I'd have to go back to the books, and I'm like, why don't I just record a video of myself doing this part of the lecture? I'd just go back and watch the video. I'd rather do that than read a book. And that's where the YouTube videos came from. It was a resource for me to be able to go back to. And then I'm like, I'll just make it available to the students. And then I made it available to the world. And now we've got like 400,000 subscribers on the YouTube channel, and all just medical education stuff. And it's just about the human body.
That's so cool.
Yeah, I love it. I was watching a video you did the other day about the lactate stuff. I'd love to talk about that if you don't mind, because, man, I love that. So, and what I also love about it is that in that video, you kind of acknowledge that the information changes slightly, so we, like, even though you're a university professor, we be talking about these amazing stuff that's been proven through science for decades, but science does change. And in things like lactic acid, and they're talking about the lactate as a metabolic waste or as a fuel, just in the last 3 decades has changed. And if you acknowledge that a lot of the early learning, from benchtop stuff, they used to talk about the fermentation, the creation of lactic acid on a benchtop in fermented foods, and use that as an analogy of this fermented lactic acid that's happening inside our body. But
Totally.
I mean, in our body, we're in again a part of that holistic system where we have these redox systems and everything. So do you want to explain what you said in the video that was really capturing everyone's attention about this thing potentially not even existing?
Yeah, you're totally right. I mean, for decades, even if I were to open up a current anatomy and physiology textbook, it would have the term lactic acid in there, and they would basically say that, if you're doing a little bit of exercise, then you utilize the ATP, the ATP stores that you have in your body. And we actually don't have a lot of ATP stores. We've got like 2 seconds worth of ATP in our cells. So, which, you think evolutionarily, that's silly, we need ATP all the time. But we've got different backup mechanisms to replenish and hold on to it and so forth. And then we utilize glucose primarily as the energy source with oxygen to produce that ATP. Now we can produce the ATP without oxygen, but we don't produce a huge amount. But with oxygen, we produce heaps. And it's happening primarily in the mitochondria. Now, historically, it was stated that if you go into the gym, you start to contract those muscles, sprint, whatever it may be, but to a degree where you require huge amounts of ATP, but you don't have enough oxygen to create that much ATP, then we use this backup energy source or this backup system called the lactic acid system. And basically, you need to understand that the carbohydrates that we eat ultimately going to turn into glucose. When glucose enters the liver cell, let's just say liver cell, but it happens in a couple of other different cell types, enters a liver cell called a hepatocyte, undergoes a process called glycolysis, where it produces a small amount of ATP, and then at the end of glycolysis produces something called pyruvate, which then jumps into the mitochondria, turns into something called acetyl-CoA, which binds with something called oxaloacetate, and it produces a whole bunch more ATP. But at the same time, it's producing these other molecules, these substrates called NADH and FADH2. And their whole job is just to hold on to hydrogen ions, which is H+, also known as protons, and electrons. Now, right now, people are probably thinking, I have no idea what that means. But the whole point is they just carry these things to a certain part of the mitochondria called the membrane. The mitochondria has 2 membranes. The inner membrane of the mitochondria has all these proteins embedded in it called the electron transport chain. And so NADH and FADH2, that's stolen electrons and protons from glucose ultimately, now hands the electrons off to the electron transport chain. And it's all in the name, right? The electron transport chain. They play hot potato with the electrons, and it excites those proteins, and then it releases the protons. So the FADH and NADH, they release the protons, and they pump them across the electron transport chain into the space between the 2 membranes called the intermembrane space. Now we've got a concentration gradient. And in biology, when you've got a high concentration on one side of a membrane compared to another, it wants to balance it out one way or another. And so if you've got a channel, then those protons will move down their concentration gradient. And they do. They move through another protein called an ATPase synthase. And as the protons move down that gradient, they create a huge amount of ATP. And you need oxygen in this process for it to happen. You produce like 32 to 36 ATP molecules per glucose molecule. So it's really effective, really efficient. Now, the whole dogma was that if you want to create all that ATP and more, that oxygen needs to be there for the process to happen. But if the oxygen's not there, it backs up to that pyruvate, and then that pyruvate turns into lactic acid. And the definition of an acid is that it releases a proton, a hydrogen ion. Now, what that means in medicinal biology is acid. So anytime we measure how acidic something is, all we're measuring is the concentration of those hydrogen ions. So if something's really acidic, there's huge quantities of these hydrogen ions. If it's really basic or alkaline, there's not many of these hydrogen ions. That's it. That's all it is. And so lactic acid, they thought, then released hydrogen ions and made the muscle tissue acidic. And therefore it was that build-up of the acid that then made the muscles fatigue, and you got the burn, and then it was a detrimental process, right? And this is something we feel in the gym when we're lifting a lot of weights. But we knew like decades ago that this actually isn't the case. This whole process, like you said, Matt, of fermentation, which is basically what it is, right? It's metabolism without oxygen. It's the same thing that yeast does, but they produce ethanol, right? We thought we produced lactic acid, but the case is it's not what happens. The pyruvate actually turns into lactate, not lactic acid. And in literature, they tend to use them interchangeably.
Yes.
And they're very different things. Lactate doesn't release a hydrogen ion, it absorbs it. It actually mops it up. So it acts like a base. So acids release hydrogen ions, bases absorb them. So when we have a look at the lactate level when somebody's doing this type of anaerobic exercise and it goes up, it's actually not the fact that the lactate's causing the muscle soreness. It's the lactate is being produced to try and stop or buffer what's happening with the hydrogen ions and absorb them and hold on to them. Then the question comes, where do the hydrogen ions come from? If it's not lactic acid releasing them, the ATP that's being produced, when it's utilized for energy, because ATP is adenosine triphosphate, 3 phosphates, you snap one off, and in the process of snapping one off, you release energy, and that's how all these things happen. In the process of snapping it off, you have to undergo a process called ATP hydrolysis. So hydrolysis uses water to snap. Lysis means to split. So it just means using water to split. And when you do that, you release a hydrogen ion. So simply just by ATP hydrolysis, you produce hydrogen ions. And that seems to be where it's all coming from. And the lactate's there to actually absorb it so that it doesn't damage us, and it buffers the whole process. So it maintains pH. Because the whole thing is that our pH, particularly in our muscles, has to be in this nice, happy, healthy balance. Around the pH of our blood's like 7.35 to 7.45. So the pH scale of 0 to 14. 14 being basic, 0 being acidic, 7 being neutral. So anything under 7 is really acidic. Anything above 7 is really basic. Now, a lot of people think, wait a minute, how come the big number means that it's basic and there's not enough hydrogen? Because remember, basic means there's hardly any hydrogen ions, acidic means there's heaps. But 14 is the most basic, which means there's not many hydrogen ions. Yeah. It's what we call an inverse logarithmic scale, and it's ridiculous. Yeah. But just to give a bit of a background, if you're reading like a patient's chart, for example, and you measure the concentration of their charged atoms or elements, they're electrolytes, right? So sodium, potassium, magnesium, chloride, calcium, whatever. Hydrogen is an electrolyte. It's a charged atom or element. That's all they are. And so if I were to take your blood, James, and I were to measure your sodium concentration, it might be sitting at something like 142 millimolar. And then your potassium might be 4 millimolar. And then your hydrogen ion is going to be something like 0.00000 whatever millimolar. So the number's really, really low. Mm-hmm. And so they don't like writing that on a chart because obviously there's too many zeros. If you mix it up by 1 zero, by 1 decimal place, that's a 10 times difference. So that's the death of a patient, right? Yeah. So they don't write it like that. Instead, they did a couple of fancy maths and turned it into pH. So the H stands for hydrogen ions. And so by using their maths, the bigger the number of the pH, the less hydrogen ions, the lower the number, the bigger the hydrogen ions. So anyway, that's a bit of a digression. But the point is that the pH needs to be in a happy, healthy range, like 7.35, 7.45. If it goes too high, the pH, so too basic, enzymes don't work. Mm-hmm. Obviously isn't good for muscular contraction and performance and so forth. If it goes too low, same thing. Has to be in the happy, healthy range. So we need buffers. And one of those buffers is lactate. And that's, again, the whole point of me talking about lactic acid not being the cause of muscle fatigue, is that the lactate that's produced is actually there to mitigate the muscle fatigue, to help us.
And that is a massive shift.
Yeah.
To talk about the fact that lactic acid would be the accumulated acid that we build up, a metabolic waste that we build up by doing our exercise, that will accumulate and loiter around, that will cause our lungs to get tight with our respiratory acidosis where we're trying to pan it out, that will trigger anxieties or worries, or might actually contribute to muscle soreness like days after. Like the thought that lactic acid is accumulating in our muscles and sitting there and as a metabolic waste that will create our DOMS. Where we've I don't know how recent really, because I've been talking about inflammation and oxidative stress in the fascia for a long time, and proving that the pain itself that comes from DOMS, it should be called DOFs or something, because it's a lot of the fascia soreness that they're finding, that it's not necessarily this accumulation of acid, and there's no changes in pH in that tissue to suggest an accumulation of this lactic acid. So to then consider that we've had this belief system about this acidic waste that will accumulate, but now to consider the fact that if lactic acid existed in that pathway, it would be a transient or temporary thing on its way to becoming a buffered thing as lactate. Now, we talked about in the literature, it says lactate and lactic acid can often be used interchangeably. I mean, to say that lactate is an acidity buffer, and lactate may be actually capable of contributing to energy and prevention of fatigue and the reduction of any sort of damage into the muscle soreness, that's exact opposite to what we've been told the whole time.
That's exactly right. And so for me, if I'm jumping around between, as an athlete, jumping from, say, a 400-meter sprint where you build that up very quickly because you're trying to get around that 400-meter track very fast, and then I jump from that to, say, something very aerobic like a marathon, I want to be utilizing as much oxygen as possible. So if I kick off a marathon and I run the first 5Ks, say, very, very quickly, and I'm building up that lactic acid, and eventually I slow it down and I find that sweet spot where I hit that like a nice aerobic area. Is that my body catching up the oxygen, or so I'm repaying my oxygen debt that I forced it into in that, say, first 5Ks where I went out way too fast, and then I'm catching it up and I'm able to then transport oxygen to these working muscles to then basically catch up and produce more ATP. Is that what's going on in my body?
Yeah, in a sense, there's a couple of things happening. So your body will generally first utilize glucose, or at least in the form of glycogen. So the stored carbohydrates that your body will have is glycogen. That's muscle carbohydrates. Obviously, starch is vegetable carbohydrates. But basically, the same thing. We store that glycogen in the liver, in the kidneys, and in the muscle. The glycogen in the liver, let's just focus on liver and muscle. The glycogen in the liver, that can be broken down and utilized by all the tissues of the body. But the glycogen in the muscle stays in the muscle. It can't get out. So whatever's in the muscle remains in the muscle. But the muscle can steal some of the liver glycogen as well. So you'll utilize that glucose pretty much straight away. That's the first energy source that you're going to use, at least in that anaerobic first point.
Right.
But then, like you said, you're going to start to get a bit of a burn, get that pain, and that pain could be due to hydrogen ions from the ATP hydrolysis. It could be due to other metabolites that have built up. Could be calcium that's doing this. Ions like hydrogen and calcium, for example, and potassium, they actually play around with the threshold of pain receptors.
Interesting.
So and I shouldn't call them pain receptors, they're called nociceptors. And there's a big difference between the two. It's actually a huge difference between nociception, which is your body's ability to pick up noxious stimuli or potentially damaging stimuli, and the experience of pain itself. So pain is, by definition, by the International Association of Pain, an unpleasant sensory or emotional experience described in terms of actual or potential tissue damage. That is the definition of pain. Huge definition. But at the end of the day, what that means is pain is in your mind. It's in your head, right? It is a subjective experience. And when I say pain is in your head, that's not me being disparaging. Pain is in all of our heads, and it's entirely subjective. Simply meaning that if I were to prick you with a pin and I asked you to rate it out of 10, and then I would have pricked Matt with a pin, same same spot, same depth, same pressure, you're going to have different pain experiences. So it's by definition subjective. Nociception isn't that. Nociception is simply the objective way your nerves pick up potentially noxious stimuli. So again, another digression, but going back, when you exercise, you release these ions, you release all these metabolites that are built up from exercise. They sort of spill in to what we call the interstitial area, so the space between cells. And they can actually play around with the threshold of these nociceptors. So instead of a neuron, a nociceptor being stimulated at a particular degree, it just drops it down a little bit. So you don't need to stimulate it as much to send a painful stimulus, which could be what's happening with DOMS down the track, is that your nociceptors, they've just been sensitized in a way. And that's the special thing about the sensation of pain and nociception, it's the opposite of all our other senses, right? So sight, taste, sound, touch, that we desensitize them throughout the day. So you walk into a room that's got a lot of noise, in a couple of minutes you don't necessarily notice the noise, right? You put your socks on in the morning, you feel it for 2 seconds, you don't feel it for the rest of the day, right? Your body desensitizes, not pain. Pain's the opposite. You have a tiny little pebble in your shoe and it's irritating, and after 10 minutes it's excruciating. So it amplifies, and it does that by dropping the threshold of these nociceptive neurons. So we think that that might be what's happening in DOMS and in the pain that we're experiencing. But to go back to your question about what's happening where you're starting off getting a bit tired, but then once you start hitting the distance, kilometers, getting into your stride, you start to feel quite good. It's also a fuel shift as well, going from glucose as the primary fuel to fatty acids as the primary fuel. And you could just broadly say that the fatty acids is more of an aerobic fuel. So over time, over distance, we need that oxygen. You do it when you're doing long distance running, for example. And is possibly one of the reasons why, because female athletes tend to utilize fatty acids really well, and is possibly one of the reasons why ultramarathon runners, some of the best in the world, are women. Like you look at the top and they're the ones that are killing it because they just utilize fatty acids a lot better. But that's what's happening. It's just the shift in fuel utilization.
Interesting. So for me, I know the other day I did a 30-minute assault bike session at a roughly 75 to 80% threshold. And when I started out, the first 5 to 6, 7 minutes was not great. I felt like this is going to suck the entire time. But then I got 12 plus through to that 16-minute mark, started leveling out, started feeling really good, and then I felt like I could go all day. So I felt like once I kind of, hit my stride, it was almost like my body had found out the right intensity that I needed to work out at that threshold where I could support my oxygen system to start, or my aerobic system to start doing its thing, instead of relying on something that's getting backed up and starting to, impede my ability to breathe and to contract my muscles.
Can I ask, when you do 75 to 85% on the bike, 75-85% of what are you referring to? Your
say like maximum output.
Okay.
Maximum output. So in that, roughly for me, I've found that if I was to do something super long, like a long, say 5-hour bike ride, and I was to take, say, my FTP and my functional threshold power output, figure out what that is. So usually that's done by my maximal effort over 20 minutes. So if I was to get onto the watt bike and I was to pump it and try and get an average wattage over that 20 minutes, let's say I've done one in most recent times, 293 watts. I can hold at an average for 20 minutes, and that's what my functional threshold power was. Then if I wanted to work out a couple of calculations, and then I wanted to ride an Ironman 180 kilometers, I was told to stick within a 70% range. So it was like 68 to 74%. Don't go above and don't go below if you want to get a good time. So then I sat at around 220 watts. That was my limit. And I sat at that 220 watts, maximizing my time, but also not putting myself so much in the hole that I couldn't run a marathon after.
Yeah.
So that roughly worked out to be around that 70% range. And that's where I knew I could work out all day long. I could last at that for 7 hours, and that's where I wanted to be. So kind of when I talk about either a 70% range or an RPE, how hard is it at the time? And every day is a little bit different. As you know, like you could do something one day, feels fantastic. Like the other day I went for a run, the first 3 kilometers was horrific. It felt like 9 out of 10, but I was running way slower than I had done on days previous. But that could be a build-up of a million different things: sleep, hydration, fuel, stress, everything that we talk about normally. So it's just trying to figure out, when these things are happening in my body, how can I best maximize my performance? Is it, should I be focusing on hydration? Should I be focusing on electrolyte? Should I be focusing on fuel? And I think a combination is probably best, and from what we can figure out. So those are the types of things that I'm so excited to kind of understand a bit more.
I'll definitely say a combination of all those things. When it comes to, obviously, sleep's super important, just getting long enough sleep and quality of sleep. Fuel is important. The way I like, and it's a gross analogy, but I like to utilize it because I think it sort of frames it nicely, is that if you've got a racing car Now, there's a whole bunch of factors that make a racing car a good, effective racing car, and fuel is one of them. And you can have the fuel that you use for that racing car have a whole bunch of different types of fuel components. You can play around with the type and types of fuel and mix the fuel to make it a more efficient race car or for it to perform better. And you can do those things. But at the end of the day, if you don't put enough fuel into the car or you put in too much fuel into the car, that's going to override anything that has to do with tweaking the components within the fuel. So the first thing I like to say is that the first thing people should note is the amount of calories. Are you hitting the amount of calories you need to be able to perform what you need? And performance means a whole bunch of different things to a bunch of different people. It's tricky with you because for you, performance may be strength one day, could be endurance the next. And like we were saying earlier, different ends of the spectrum, right? Usually when somebody trains for strength, they do low reps, they do high intensity, and they've got really long rest periods. Then when you do endurance, you flip that, right? There's no rest period. The weight or the intensity is low, and it's just totally opposite.
Well, that's exactly right. When I typically would, if I was going to do an aerobic session in the morning and I was going to go 10K run, I could do that fasted. I just have some water before I go, get up, get running, feel great, feel fine, feel like I can do it at within 5% of my max ever effort. If I want to go to the gym and lift a heavy back squat or a heavy deadlift or a heavy front squat, I have to have fuel in my body most of the time, otherwise I feel like I'm going to pass out. And there have been plenty of times where I've done a clean or a front squat or something that's on that front rack position that just is bearing load on me. And if I haven't had any fuel, I'll start to get a little dizzy. And I'm just, okay, so now I know that I have to fuel prior to that. Otherwise, I will start to just feel everything just drain out of my brain. To take me down to the ground.
So what is that? So when we, so James was saying you can get up and do a fasted cardio or fasted run and ride and that sort of stuff and do that no problem as long as he's had enough water and that sort of stuff. But then to do a gym session, he needs to eat before. How long? I mean, are we talking muscle glycogen? But we wouldn't.
Yeah, I'd say blood glucose.
Yeah,
I'd say blood glucose.
And is it because with the cardio he's doing more of the fatty acid oxidation to fuel that?
I would say so. Yeah, I would say so. And we tend to get. I mean, our blood glucose changes with our circadian rhythm, regardless of actually whether we're ingesting or not. So even when you're fasting, there tends to be early in the morning a little spike in our blood glucose, even though we haven't taken in any glucose. And so what's potentially happening is the fact that if you're going for your run, you're utilizing fatty acids like you said, Matt, and the glycogen stores may be predominantly being spared, and then you're going and doing a weight training session, your blood glucose levels. Now, the glucose is obviously, it either gets used or it gets stored. And if you've just finished a run and you haven't eaten, you're not replenishing any lost stores, then you go into the gym, you start to utilize that anaerobic basically capacity where you need the glucose, you need glycogen, you don't have it. Your blood glucose levels go down, your body tries to back up, you can't do it. You get dizzy, your blood pressure changes, and just don't feel great.
Now, on the back of that, for other listeners, not just about James, but for other people that might then think, I'm going to go do weights and I'm going to do that fasted so I burn more fat. Is that even a possibility? I mean, if someone's doing the weights, are they even going to be burning fat during that weight exercises, even if they're fasted? Is it worth it, or are they better off just getting some blood glucose and doing a good quality workout and celebrating what their body can do?
I would say the latter. But again, everyone's goals are different. At the end of the day, if it's about weight loss, then the equation is calories in, calories out. So you reduce your food intake and you increase your energy output, and that's the equation. I know it's a simple thing to say, and for some people it's obviously far more difficult because of obviously issues with relationships with food, relationships with exercise, and for many people changing one or the other is difficult, but at the end of the day that is the equation. If somebody's goals are speed, strength, hypertrophy, then it requires different things. Generally, you need more calories for those because you need to be able to perform appropriately.
Yeah.
That's I think that makes a lot of sense, and I guess it's really dependent.
Oh, it is. It's great. No, so another thing I was curious about before you mentioned, we're talking back to the hydrogen bit. We're talking about these hydrogen ions, and we're talking about the hydrogen as an electrolyte. The positive charge, because like we're talking about the electron transport changes all the negatives, and then it creates the big electrode potential for the positive switch over.
Yep.
Where do other electrolytes? So you mentioned before that we think of sodium, calcium, magnesium, potassium. How do those other positively charged electrolytes contribute to acting as acidity buffers, for example? I know that we talk about them as acidity buffers, but I mean, if they're the same positive charge as a hydrogen, how can we explain that?
So the way I like to look at it is when it comes to pH, it's all got to do with the quantity of hydrogen ions. But there are ions, like you stated. So ions are simply charged atoms or elements. They can be positive or negative. And we usually ingest them in the form of salts. So basically, electrolyte is the medical term for salt. And there's many different types, like table salt, sodium chloride. The whole way that electrolytes work, or salts work, is when you put them in water or a fluid, they split apart and now they have a charge. So sodium inherently has a positive charge and chloride has a negative charge. But when they're together, they share the positive and the negative comes together. It's this perfect snap together relationship, and that's sort of how electrolytes work. So we ingest them as salts, and there's many different types: sodium chloride, potassium chloride, and so forth. We take them in, and then once they're in, because remember, like 60% of our body is water, and our blood, which ultimately is where everything's going to be going, that's mostly water as well. So the plasma, mostly water. So all these electrolytes turn into the ions. And so the main point of, and there's many things that many different ions do, but one of the most important things that they do is that charge that they have, regardless of whether it's positive or negative, attracts water. So the great thing about water, the reason why we love it and we need it, is because it's H2O, 2 hydrogen, 1 oxygen. So the 2 hydrogens have a slight positive charge and the 1 oxygen has a slight negative charge, which means the negative oxygen will attract all the positive ions and the positive hydrogen will attract all the negative ions. Primarily because the ions are in the water, wherever the ions go, the water follows. So that's how you should think. Wherever salt goes, water follows. And I tell my students, you sit at a bar, you have some chips, you get thirsty. That's why they have peanuts out at bars, get thirsty, you drink more beer, right? That's the whole point. Wherever salt goes, water follows. And that's how diuretics work. So when people have like congestive heart failure and there's too much fluid building up in the body and they get edema, which is just fluid sort of leaking out of the blood vessels and filling the tissues, they give them a diuretic. And a diuretic simply just makes you pee out those ions, sodium and potassium, magnesium, and water follows. And that's how you reduce the water content in the body, just through that. So that's the main function of these ions. And one of the reasons why people take electrolytes is for its ability to maintain hydration. And it's actually the way that endogenously or intrinsically the body regulates hydration, is that if you have a cup, or let's just say you've got a cup that's got half a litre of water in it, big cup, and it's got 10 grams of salt. Let's just say you were to take out half of that water. So there's now only 250 mils of water, but still 10 grams of salt. That cup is more concentrated with salt now. It went from being less concentrated to more. Simply just by taking the water out, you've changed the concentration. You haven't touched the salt. So you can have the correct absolute amount of ions in your body, electrolytes in your body. It's just the fluid that's changed. And you then become too concentrated. And what happens is your hypothalamus at the bottom of your brain, it's got what is called chemoreceptors or osmoreceptors, which picks up the concentration of stuff. And it simply picks up the fact that the concentration's gone up. And straight away you go, I'm thirsty. So you have no idea what the concentration of salt is in your body, but you go, oh, I'm thirsty, because your hypothalamus has told you. But that's not the only thing that it does. It releases a hormone called antidiuretic hormone, ADH. If you're in the US, it's called vasopressin. And that travels to the kidneys and literally puts little holes in the filtration units of your kidneys to reabsorb water back into your body. So you hold on to more water. So a whole bunch of things actually happen. It releases aldosterone, which is another hormone from the kidneys, from the adrenal glands of the kidneys, and that reabsorbs sodium And because sodium's an ion, water follows. So you reabsorb water back into the body. So these are all the things that happen to maintain your hydration status.
Yeah.
All because of the concentration of ions in your body fluid.
And through hydration, we can then reduce the concentration of the acidic ions that is making us...
So going back to your question about changing the pH and buffers.
Yeah.
So there's a couple of different types of buffering systems in the body. Probably the most important one is the bicarbonate buffer system. And bicarbonate ion is an ion as well. So that's HCO3. And this is I love this, there's an equation, which I really love, because it's really important when it comes to, one, pH management, but also the role that the lungs play and the role that your kidneys play in maintaining your blood pH. So you take a breath in, most of that gas is nitrogen, then oxygen, then carbon dioxide. That's the concentration, right? Nitrogen, forget about, we don't really play around with unless you go deep diving, and then the pressure changes and you start to use nitrogen in very strange ways. But the oxygen we bring in jumps into our bloodstream, it goes to the tissues of our body. With glucose, we produce all that ATP, and the exhaust that we spit out is carbon dioxide. So carbon dioxide is an exhaust of our cells. And as an exhaust, we don't want to keep it. We want to spit it out. And the way that we spit it out is by throwing it back into the bloodstream. But the thing is that carbon dioxide, when it mixes with water, it produces something called carbonic acid. And I said the definition of an acid is something that releases a hydrogen ion, which makes your blood acidic. So if you have too much carbon dioxide in your bloodstream, your blood becomes too acidic. But luckily for us, we have lungs. So if our blood does become too acidic, we hyperventilate and blow all that carbon dioxide out. And you see this with some patients. So people who have chronic obstructive pulmonary disease called emphysema, which is a COPD, they have a lot of difficulty breathing out. So most of these individuals have smoked their whole lives. The cigarette smoke and some of the chemicals break down the elastic tissue in the lungs. And what that means is that when you take a breath in, your lungs stretch open, but without the elasticity, it doesn't snap back. So a lot of the main way that we breathe out is the elastic recoil of our lungs. Like stretching a rubber band, you let go of it, just snaps back passively. That's the way we primarily just passively breathe out. Stretch it, snap back. But if you've got emphysema, it stretches, doesn't snap back. So for every breath in, they hyperinflate. But the carbon dioxide remains, and they're called carbon dioxide retainers. They just hold on to the carbon dioxide, so their blood becomes acidic. And then you see them trying to hyperventilate and trying to change the carbon dioxide levels. So the lungs do change, and that's the reason why when you do exercise, you breathe so much. It's actually not as much about getting oxygen in. Yeah. It's about getting carbon dioxide out. We're really good at getting oxygen in. That's rarely the issue. It's I'm breathing so I can get that carbon dioxide out.
And so when we train, for instance, let's just say I have a 10K PR of 55 minutes, and then I want to get that down to 40 minutes. In the process of training, I want to gain this adaptation where I can be better and be faster. So when I'm putting that type of system under stress, muscles, lungs, blood, all that type of stuff, what actually happens in that process? Am I building more capillaries? Am I building more red blood cells? How am I becoming more efficient?
Yes, the answer is yes.
Great.
Yeah, all of those things.
So and more.
And more. Yeah, so in terms of am I getting more efficient in my utilization of energy? And so all these things, what is the process of going from 55 minutes at maximal capacity to doing 40 minutes? What are some things that I could do? Obviously running is going to help, but what's happening to my body to become more efficient?
So you hit the nail on the head, is that adaptation happens in response to stress. Mm-hmm. And so you need to stress the body. And again, everything about biology is, the term that everyone needs to remember is homeostasis, the happy, healthy range. Everything has a range that we can sit within. But if it goes too high above the range, not good. Too low below the range, not good. But we can push it either way just a little bit and the body will respond. So an example I gave was the dehydration, right? We don't have enough water in the body. The body responds to that stressor. The lack of fluid was a stress and the body adapted and responded to it. Now, luckily for us, when it comes to exercise, which if you think historically, evolutionarily back, we needed to be fit and strong so we could hunt and we could get food and we could forage and we could do all those things. We needed to be fit. And so we needed to be able to adapt and change to the environment. And the great thing about human beings, one of the reasons why we're so successful, super adaptable. We can eat nearly anything. Honestly, like you have a look at other animals and they've got very specific, narrow diets. We can eat so many different things and adapt. And that includes the way that we can train. So we've got huge adaptability, but we only adapt in response to stress. And so the trick is to try and stress your body to the point where it's not detrimental, which is hard for an athlete because that more training is better in their eyes, right? And it's hard to not train because you think I'm not doing anything active because by definition you just want to keep going, getting better. And it's hard to have that thought, I'm going to sit down and recover, because it's so passive. It feels like you're not doing anything and it's not beneficial. But it is hugely beneficial. But it's about figuring out your stresses. And you probably know it better than most people. You know your body better than most people. But generally speaking, if you stress your body to the point, and this is just where you keep pushing it. So you try and up the intensity a little bit, up the heart rate a little bit, increase the load a little bit. And what you'll find is that these types of stresses, the body goes, oh shit, I need more oxygen. I need to utilize glucose better. I need to now shift over to fatty acids, lipid lipolysis, and then utilize fatty acids. And it starts to sort of figure these things out. And you said it, like you create new blood vessels called angiogenesis. So new blood vessels, which is a huge thing, which is super important, because you might think a small amount of capillaries being produced, it actually equals like hundreds of kilometers worth of the ability of gas exchange. So it's super beneficial. So angiogenesis, great in the context of exercise. Angiogenesis can be bad in other contexts, but in exercise, really good. Mitochondrial biogenesis. So the mitochondria is what's utilizing that oxygen and undergoing the Krebs cycle to spit out all that ATP. And you can stimulate that through stresses. So there's been some studies looking at things like exercise on the back of fasting. And that's a bit of a stressor because your body goes, oh, I don't have enough fuel resources, what am I going to do? And it responds through mitochondrial biogenesis. But the trick is to make sure that you stress your body enough during the training, but obviously not in the competition, right? So the hardest part should be the training. The competition should be
the glory.
The glory, absolutely. Another point I'd like to add, which I think is really interesting, is they did a study looking at what was the cause of athletes to stop doing a particular movement. Was it muscle fatigue? Was it pain? Or was it their perceived rate of effort? Now I want to ask you, what do you think stops you if you're at the games, there's a workout you need to do, and the thing that makes you give up is what?
Perceived.
Yeah.
It's my perceived rate of effort.
Yeah.
I think, should I be going this hard? Am I going too hard? And it's usually your brain telling you, hey, here's how you feel, and whether it's physically that happening or not, it's your mind typically first. Your body could probably go for double the time.
Yeah,
you know?
That's it. That's what they found. They found that muscle fatigue rarely is the case. So people would say, no, I can't do another rep, or I can't generate the force required to do the movement. But they'll do that test and they'll go, no, you can actually generate 3 times the force required to do that. So it's not fatigue and it's not pain. They all sort of play a role, they all sort of coalesce together, but it's the rate of the perceived effort where you go, I don't think the effort I'm putting in is worth the outcome, or I don't have the motivation to put in the amount of effort required to complete.
Or your perception of the nociception signals, because when we talked earlier, the difference between you're getting signals coming back to say, hey, something's happening here. The stress nervous system sending a message saying something's happening here. You have that decision point to make, is this a bad thing and pain, or is it something I'm going to push through? And often it's your perception of those signals. So we talked about the other day, the first thing we should try to do is thank them. So the first burning signals, the first sort of signals of stress and that through our muscles, we should be going, cool, thanks for that.
Reframe it.
Yeah, I got the signal that there's something happening down there. By the way, I'm doing this on purpose. Yeah, this is my plan.
It's so true though, because you're going against, hundreds of thousands of years of evolution to push through that pain. Because again, that definition of pain, unpleasant sensory or emotional experience described in terms of actual or potential tissue damage. So while there's a lot to unpack there, it's an unpleasant sensory, so a feeling, or emotional experience. So emotional pain, so even pain from heartbreak is pain, right? It's the same. It is actually the same. Described in terms of actual tissue damage or potential. So it's a warning system. So it is really hard for us to ignore our warning system for pain.
Absolutely.
Really, really hard.
It's so funny.
Can I tell you something?
Yeah,
No, you go.
No, hit it.
Oh, no, because there's some fascinating stuff, again, back to the start, around lactate. So, for example, lactate is very important for memory and very important for imprinting certain memory. And what this suggests to us that lactate actually plays a major role in things like PTSD or trauma and that sort of stuff. But it's also potentially a very important role when it comes to training, muscle memory. That training when you're so exhausted that the training just kicks in. And if you notice, with a lot of these intense stuff like the military and that, they'll get these people into that state of lactate when they then make them rebuild their gun or whatever, So we learn these skills under lactate. And so what can also happen is we can imprint memory. So you can have bad experiences while you're getting this particular signal from a previous event or getting hit by a car or something like that. Then you can get these signals again. And the combination of your posture, the event with the memory and the lactate is enough for you to like, oh shit, I've got to hold back, I'm going too far. So this is a very important part when we understand how effective lactate is as part of your training and reinforcing positive muscle memory or reinforcing positive skills with that lactate. Because when you're in that autopilot mode in the middle of fatigue or exhaustion, I used to do a lot of work with a lot of UFC fighters and things like that. There's some of the guys actually fight significantly better when they're unconscious. Like they just, this autopilot kicks in and all of a sudden everything drops, they just go. So having that's another thing that you learn through training. So.
It's flow. It's finding flow, and I think for a lot of people, finding flow, they talk about this state of flow. When you can get there, it's fantastic because you feel like superhuman and think like nothing is going to slow you down. And I know the feeling, and it's fleeting, but I know the feeling when you're doing a workout and you're in lane 5 and you've got 4 lanes left of you and you've got 5 lanes right of you, and you're just thinking to yourself, you just have that premonition that you're going to crush it.
Yeah.
It's a great feeling and it's fantastic. It's hard to find, but once you do, it's amazing. But the thing that you were talking about there that resonates with me so much is that I went to the CrossFit Games in 2016, 17 and 18, didn't have a great time because I was so hesitant that I would go out too hot. I wouldn't pace it correctly. I was hesitant to pick up the weight a little bit quicker, run a little bit faster, jump up on my pull-up bar 5 seconds too early, and then...
Hesitant because you're worried about making a mistake?
Hesitant that I'm going to go past my red line.
Gotcha.
And then crash and burn and be left with nothing, come out hot, get to round 5 of 10 in first place, and then finish in 10th place.
Yeah.
I was always very hesitant about that because, I don't know, maybe I didn't want to make a fool of myself. Maybe I put pressure on myself that people expected these things of me. And then if you're worrying about those things, you're not finding flow.
No.
I guarantee you're not going to find flow. When I went in 2019, completely different story. I went in there thinking, you know what? I didn't do well in 16. I didn't do well in 17. I did okay in 18. But not great. Not where I wanted to be. And I've already sucked before, so it doesn't really matter if I suck again. And so all I did was I just rolled the dice and I said, you know what? I said to myself before each workout, I said, if I shoot this out, I'm going to back my fitness. My coach backs my fitness. They've told me I have the ability to be on the podium this year. I'm just going to roll with it and I'm going to go out 10%, 15% hotter than I normally do, and let's see if my fitness can hang. It hung, and I wish I had done that every other year because I felt just as physically. I felt my lactic threshold was just as good in 2018. I thought my VO2 was just as good. I thought my strength was just as good. I thought my power was just as good in 2018, but the results were vastly different. And the only difference was my mindset going into it, and that was it.
It's amazing how people neglect that.
100%.
They train their body so hard without training the mind, and the mind is a part of the body.
Yeah.
And people, it speaks to the point of the mental health crisis, not just in Australia but all over the world, is that people don't acknowledge that mental health is health. And so you do need to train your mind if you're an athlete, if you're going to be training your body at the same time for performance, because it's like you just perfectly highlighted. Your body's not going to do what you want it to do unless your mind allows it. And it's about that whole reframing. If you think I'm going to feel pain early, you're going to feel pain early. It's just the case. We can alter the way we experience pain by just putting a smile on our face, by laughing, even though nothing's funny. By distracting somebody, we can alter a painful experience. And pain is obviously one big part of why people sort of give up during movements and workouts.
Interesting.
Yeah, so it's about that reframing. And it also comes back to skill acquisition, and also what you were talking about, Matt, where you sort of go on autopilot. You want to train yourself to the point where you can go on autopilot, where your motor patterns are just so finely tuned that you can just go, I'm just going to let myself go and do what I need to do. You don't need to focus on it. That's what training was for. Training was to keep your mind on the task and focus. This is where the hard work goes in. And again, intention to train is, and not just intention to train, but your intention during training is super important. So instead of just going in and going, I'm going to do chest and back, I'll do a hypertrophy session today, chest and back, and then I'm just listening to whatever podcast which I do it all the time, listen to whatever podcast in the gym. I'm not even paying attention. It's just like, I just need to move this weight 12 times in this direction, right? But if you have the intent and you go, okay, I need to move this weight, I need to feel the muscle control, I need to feel the way the muscle moves, that actually is beneficial to the performance of the individual.
You know who said that the best?
Who?
Arnold Schwarzenegger.
Did
he? He did say, he goes, I was lifting the same weights, the same sets, the same everything as the other guys in the gym as me. He said the one thing that I did different was I thought about it more.
Yeah.
I thought about getting the result I wanted in every contraction more than everybody else, and that's why I was better.
Yeah.
And we were just like, whoa.
Yeah, that intention is super important, and people forget about it. And it's easy to forget about it, especially if you're an athlete and you train so often. I'm sure it's difficult. There'll be times where, particularly, obviously running is a little bit different because you can go on autopilot in that sense. But when you're doing a strength session, for example, to just go, I'm just going to move the object and that's it, without the intent behind it.
Oh,
but it's super important.
Yeah, exactly. And the same thing goes for like Olympic weightlifting. There, you can, if you've done enough, or you've done your 10,000 hours, and now you're a specialist and you're almost perfect. No one's ever perfect, but if you do. You can almost go on autopilot, but once you're getting to the upper end of your threshold, you have to focus. There's no one walking into a 95% clean and jerk or a snatch thinking, I'm just going to go through the motions here. You're thinking, oh man, this is my upper limit. If I don't focus here, there's no chance of me getting it. So it's a very interesting thing. But the other funny thing, part of it is the focus, and it's usually the setup. The setup of all these things is the foundation where you can think, but when you do a snatch, it's too fast for you to think. You cannot think about it. If you think about the 95% snatch during the snatch, there's no way in hell you're going to make that lift because it happens too quick, and you have to then rely on those motor patterns that you've honed in for those 10,000 hours. But your preparation leading up to that, the 15 seconds before you do that lift, that's just like, where's my weight? Where's my grip? Where's my eyes looking? Where's my back? Where are my lats sitting? Are they down and back? Am I over the bar? Great, I'm here. Good, go.
Totally matters.
And then it's just, next thing you know, the bar's overhead is like, did I get it or didn't I?
Yep.
Like, oh, I got it.
When it comes to that skill acquisition, which you sort of train so that then you can do that autopilot once you're in the movement. Like you said, snatch is super quick. So you have to be on autopilot in that sense. In the first instance with skill acquisition, it's about the perception of it. So that means you need to think about what you're doing. You need to view in your mind's eye the movement that you're performing. And so that's an important part. Then the next important part, so usually in the first instance, that's what you've got to do early on. Then when you become a bit better at what you're doing, it's simply just like you said, those 10,000 hours. Just keep doing it and doing it and doing it. And you reinforce those motor patterns. Like our brain is so plastic. It has the ability to adapt and improve and change. And if you just keep doing that same movement over and over and over again, slight changes will lead to large benefits.
Yeah, is this what you were showing me before with the brain? Was it a brain cell that was making a link?
Yeah.
It was making links, and so you start to create these links, and those links become stronger and stronger and stronger, and we basically build these patterns. It's like when you do the bench press for the first time, and you're like this, and you're like, whoa, there it is.
Yep.
And then you come back down again, and then eventually it's just like, I could do this any day of the week. There it is.
I can't wait to take you to Ken Ware's place too, because Ken Ware, what he did, he was, excuse me, so he was full power lifter, going for all the records, and he was also a bodybuilder trying to do the Mr. Universe and all that sort of stuff. And then he basically got his whole world blown apart by a couple of old buggers that gave him a broomstick and said, go and do that squat with a broomstick with no weight and do it really slow but symmetrical. And he couldn't even move. And it just mentally wrecked him. So then he went away and took away all of his weights, and until he could do 10-second reps perfectly symmetrical. And it just messed with him for a long time. And he eventually quit everything. Wow. Because he was just like, I'm a failure, I'm a fraud, blah, blah, blah. And then until he was about 6 weeks out from when he'd normally compete at the Mr. Universe, and he'd been doing the whole off-season, just doing these 10-second reps, and he realised he was in better shape than he was for his other... And he went in and won that one. Yeah. And he'd never won one before, but he'd all done and all this slow 10-second reps. And so what he does when you go to see Ken, he's like, every millimetre matters. You just go through, we get symmetrical. We just got to be perfectly symmetrical. And the freaky thing is when he loads you up with weights, it was very easily to be reactive. So you can react against stimulus, but to actually be proactive with very little weight and just see how much control you have over your pecs or across your deductive, and it messes with your brain so much. But learning at school, you can suddenly become more symmetrical and calibrate with all your different injuries and that sort of stuff. So I think that is something we'll do for you as well.
It's one of the reasons why we wear a belt, like a weight belt. It's not just to increase that intra-abdominal pressure. It's also to provide us with sensory feedback.
Yeah.
Because obviously if I were to tell you to sort of brace your core right now, you could do it. But if you put your hands on your core and then to brace against your hands, it's a lot easier to do. And so when you put on a weight belt, you don't even have to put it on super tight. You just have to put it on, relatively tight. And it just gives you proprioceptive feedback, sensory feedback to go, oh, I'm going to brace against this.
Yeah.
And so that's one of the reasons why some trainers will, they'll put their hands on the rhomboids and say, squeeze my fingers with your scaps. Well, it's just providing that sensory feedback, which we don't often get.
Yeah.
So, it's okay to be in the gym and look at yourself in the mirror, and lift and see what muscles are contracting. Look at the muscles you're contracting. Feel the muscles that you're contracting.
Yeah.
It's all part of it.
Yeah, that's super interesting. And I think I would love to just quickly jump into a little bit of time under tension for muscle building.
Yeah.
So that probably goes to the 10-second reps. I think a lot of the times, and especially with CrossFit, if we're doing jerks, it's literally drive here, get it to here, and locked out as quick as possible. There's no time under tension there. It's just powerful, bang, bang, get from A to B as quick as you can, and then get back down. When we're doing muscle building, and we've found that there is, maybe a semi-sweet spot somewhere, and it's different for everybody depending on the goal, but a semi-sweet spot for hypertrophy, and we want to build some muscle. So trying to, get around that, maybe that 40 seconds of work to 50 seconds of work. Some people have said that's fantastic. Some people, disagree. But when we're building muscle, what are we actually doing to the muscle? Let's say I want to build my bicep, which don't grow very much for me, and I've been trying for years and years and years, but it does not work, and you know what? It's okay. But if I want to build my bicep up, I'm going to stress it, like we've talked about before, to get an adaptation. What am I doing to my bicep muscle to then rebuild it to make it bigger?
Yep. So there's 3 major types of hypertrophy. So you've got connective tissue hypertrophy, you've got myofibrillar hypertrophy, and you've got sarcoplasmic hypertrophy. And they all sound like quite complex terms, but they're not. If you think about a muscle cell, right? So a muscle cell will be surrounded by connective tissue. Connective tissue holds things together, binds things, and anchors things. Now, connective tissue isn't static, it's dynamic. You can change connective tissue. And so 30% of a muscle is connective tissue. So you can grow that, increase the collagen deposition, increase the different types of connective tissue fibers that are present, and you can increase this, because all hypertrophy is increasing the size of a muscle. It's not about strength, however, size correlates with strength, but it's just increasing the size. So you can do it through connective tissue hypertrophy. You've got sarcoplasmic hypertrophy. So because in biology we like to be bastards, we just create all these weird Latin and Greek terms. And instead of saying muscle, we say sarco. Sarco means flesh. So a normal cell will have the inside of the cell, the cytoplasm, which just means the goo in the cell, right? But a muscle has the sarcoplasm. It's just the goo in the muscle cell. So it's all the stuff inside, which includes mitochondria, it includes the nucleus, it includes all the organelles like the sarcoplasmic reticulum and so forth. It's just those things.
Golgi body, is that in there too?
So the Golgi, the Golgis are there.
Yeah.
You've got the endoplasmic reticulum, which in the muscle is called the sarcoplasmic reticulum, but you do have the Golgi, and the Golgi just like, packages stuff.
Cool.
So
I remember that from year 12.
Yeah, good. The Golgi bodies is what the Golgi apparatus produces.
That's right.
Yeah.
Okay, it's coming back.
Remember, the Golgi is the post office, packages things up and sends them away. But if you can increase the volume of those things, so you can increase the nuclei, so the nucleus, and that's important because it's the nucleus that creates proteins.
You can
proteins
increase,
that contract.
so you can increase the nucleus inside that cell. Can you make more, or does one cell only have one?
So a muscle cell generally will have one, maybe two, but there's these cells called satellite cells, and what they can do is they make new nuclei. And so if you stress a muscle cell enough, it goes. Because remember, the whole point of growing muscle is to respond to a challenge. And the challenge is usually some force. Because muscle tissue, there's 3 types of muscle in the body. There's skeletal muscle, which attaches to our skeleton. That's what you use when you're doing CrossFit and running and all that type of stuff. You've got cardiac muscle, which is just your heart. And then you've got smooth muscle that lines the inside of all your hollow structures. Got digestive tract, reproductive system, renal system, so forth. But they all do the same thing. They all contract, which means they all shorten to move something, right? So and it does it through proteins. Now, if you've got some sort of force, like you're doing some eccentric movement of a bicep and it's sort of challenging that muscle and it goes, oh shit, I can't move this weight, I need to respond. It needs to do one of those 3 different types of hypertrophy, connective tissue, sarcoplasmic, and then myofibrillar, which is now increasing the amount of proteins that you have, the contractile proteins, the actin and myosin. You can only increase the amount of those through the nucleus. The nucleus holds the DNA, and by transcribing and translating that DNA, you create proteins. It's the only way. Now, if you've got a lot of stress, the muscle cell goes, I need more nuclei. So it turns the satellite cells, which are what we call quiescent cells, that just means they're sleeping, stimulates them to make more nuclei to make more proteins. And so then you can have myofibrillar hypertrophy. And so there's 3 different types. But at the end of the day, there's different things that can stimulate hypertrophy. And it can be tension, so mechanical tension. It can be metabolic stress, so not having enough glucose or fatty acids available, for example. And it can be direct damage, so trauma to the tissue. But at the end of the day, you're not going to get muscle growth just from trauma. You're not going to get muscle growth just from metabolic stress, but you will get growth from the tension. So it's all about load. Wow. So hypertrophy, this is just a long way of me saying that it's all about load and volume for hypertrophy. Hypertrophy training is fail-safe. You do between 5 to 30 reps, you'll get hypertrophy, right? It's just about load. And you don't even, and it's about the load across the week. So it's simply like you could do a huge volume on day 1 and not do anything for the next couple of days, and then do a little bit on day 4, or you could spread it out every single day for the whole week. Doesn't matter. You'll get hypertrophy.
And I guess that's why some people may say, hey, this works really well for me. Lifting heavy 2 to 3 days a week is great for me. That just might be that personality type. Yeah. But then someone says, I get better results, whether it's good for them or not, but then I get better results working out 3 days on, 1 day off. So everybody's a little bit different in that respect, right?
Yep. Yeah. And there isn't like one hormone that drives it as well. Like a lot of people think it's the androgens, but we know estrogen's the most proliferative of all hormones, especially for stimulating connective tissue. Oxytocin's one of the most effective ones at supporting fascia and collagen. And so what Dr. White was talking about before is like, if you have a look at those anatomy physiology charts, the dudes with no skin, the red meat and the white meat. So we look at all the connective tissue as the white meats, all that fascia and all the bone and all that sort of stuff. That'll all involve, that's where you can find the connective tissue and collagen. And then the red meat's looking at myofibrillar sort of protein. So we feed the red meat often with our calories and that sort of stuff, and we got to rebuild that white. But you can see if you can't build an infrastructure to hold the muscle. So this is why it's so important to understand that we need to regenerate the connective tissue. We need to get more fascia. We need to get more collagen in that built to be able to hold the meat. Because it's almost like building the sock, and it swells. There's a wicked paper. I love this one paper. There's a young dude from America, Michael Roberts. He's part of the ISSN, but he did this wicked paper because he went and got the ISSN's protocols for hypertrophy.
Yep.
And he went and did this massive study where he followed those exact protocols for hypertrophy of everything we know through science that works. The coolest part about the study is 30% of the people in the study lost muscle. 30% of the people got bugger all, but 30% of the people really built muscle. And what became fascinating is he went through and analysed the differences between the different groups and could find that the guys that actually lost muscle, they were missing one of those three parts. They either couldn't do the protein, they couldn't build the protein, or they couldn't build the collagen or whatever. They just were losing muscle because they were missing one of those three elements.
You need to be in an anabolic state, right?
Yeah.
And so if you don't have the appropriate amount of calories, how can you build things up, right? Same thing when you don't have enough fuel in a car, you're not going to get from point A to point B.
Yeah, it's crazy. And the satellite cells too, another interesting thing they found with that is when that mimicking the injury and the trauma, like when the bodybuilder goes and they train for that pump and they get that swelling in the pump. So what's actually happening there is the fascia and everything that gets so kind of like swollen and stretched, it becomes permeable. And then that combined with the inflammation and then all this extra nitric oxide that comes from the dilation of the blood vessels, I mean, that resembles injury, a swollen tissue. And then the permeability of that fascia allows those satellite cells to migrate, and that's a big stimulus to say, let's grow. And then if you're eating enough calories and that, it'll drag that protein through and everything to support that protein synthesis. But you need those three components happening at once.
That's the reason why ice baths aren't great after hypertrophy training, is because it just blunts all those effects.
I've heard that a lot. I've been listening to a lot of podcasts about that recently, and I love it. I'm so fascinated by it. I think before we finish off, and I know this is we could probably talk for just as long as we just spoke then, but I want to just finish this one off just talking about cramping.
Oh.
We want to know about cramping.
It bugs the hell out of me, cramping.
We still don't know what's going on with
Exactly.
I'm so gled you said that.
Yeah.
I was starting to feel like an idiot.
Because I remember, and everyone's probably experienced a cramp before, and I think some people are more susceptible to cramping. Like I've got a friend, I'll go out surfing, and he'll just be sitting on his board. He hasn't done anything stressful. Who knows? He could be hydrated. We don't know. Could not be fueled. Who knows? But sitting on a board, and his hamstring will just cramp 2 or 3 times a session. I might get a cramp if I dig myself a huge hole, buckle myself in training all day long, and then I might cramp.
Yeah.
And we can never really figure out what exactly it is, but dodging snipers at the end of a marathon, that's the last thing you want to do.
So we know that the ions play an important role, because when it comes to muscle contraction, I always tell my students, you need calcium to enter a muscle cell for the muscle cell to contract. So calcium makes muscles contract. Doesn't matter what type of muscle, heart, skeletal, smooth, you need calcium. But you also need magnesium, especially for ATP, for it to do. Without magnesium, ATP can't do its job, so you need magnesium as well. But you also need sodium, because sodium creates what's called an action potential, and that allows for, and you need to, let's take a few steps back. You've got certain types of tissue in the body called excitable tissue. So they're tissues that can do something. So a neuron can send a signal. A muscle can contract. A gland can release a hormone. So they're all excitable tissues. They've got the ability to do something. But they're not always doing those things. They're at rest or they're doing something. So there needs to be a stimulus to tell them to do that something. Okay, so at rest, these cells, these excitable cells, what they've got is on the inside of their membrane, it's slightly negatively charged. On the outside, it's slightly positively charged. And the way that works is because it's got a whole bunch of positive charged sodium outside, and it's got some positively charged potassium inside, but the potassium leaks out. So it's carrying that positive charge with it. So they're both actually positively charged, but if you compare the inside to the outside, the inside's slightly more negative compared to the outside. All right. So that's a resting cell. That is there, and it's called the resting membrane potential. It has the ability to do something. It's got the potential for something to happen. So all you need to do is, because the inside of a cell is slightly negative of an excitable cell, you've got to make it positive. And you do that by throwing a positive ion in. It could be sodium, it could be calcium, right? So generally, it's sodium that you chuck in and it gets excited to do its thing. But again, it could be calcium. And this is neurons as well. So in the brain, it's the same thing. You can do the opposite. You can stop an excitable cell from doing its job by making it more negative inside. So you could take more potassium and chuck it outside, or you could block the ability for positive things to go in. This is how hundreds of drugs work. Drugs that like inhibit the nervous system or activate the nervous system. Drugs that inhibit muscles from contracting or activate muscles contracting. They simply activate or block the movement of positive and negative things inside the cell. So going back to cramping, the muscle won't cramp unless it's positively charged inside. So something's made it positive. So it could be an ion imbalance. So maybe it's a potassium flux, a sodium flux, a calcium flux, a magnesium flux. And we're quite confident it's one of those things. But you say that, then you supplement somebody with these things and it doesn't benefit them. Like magnesium doesn't really benefit too much for cramping. And we think it will. And same with sodium and so forth. So there's got to be another part of the equation.
Well, then we got the concentration then we talk about the dehydration aspect.
Yes.
And we just So then again, talking about the dilution and concentration around the water.
Yep.
That bugs the hell. I mean, a lot of our data about cramping came from bloody coal miners, and they're surrounded by carbon, which is positively charged. It just freaked me out anyway. No, you know what I mean? It's like this messes with my mind because there are so many different types of cramping. But at the end of the day, it's a neuronal, like it's a nervous system excitement, like it just freaks out in that little area.
So it could be the acetylcholine as well at the neuromuscular.
It's local as well. That's what
Yeah.
spins me out as well. It might be in one calf.
Yes.
And then you're just like, so hang on, this whole body system of electrolytes and water doesn't make sense if it's just there.
Yeah.
You know, that sort of stuff bugs me.
It could be a lower motor neuron issue with the acetylcholine release. Maybe there's an issue with acetylcholine. So you've got, in order for a muscle to contract, you've got 2 neurons coming from the brain. That's it. They're super long neurons. So one going from your cortex, your motor cortex of your brain, it goes down to your spinal cord, and then at the spinal cord, it synapses or talks to the second neuron that goes out to the muscle. So just 2 neurons for each muscle to contract. Amazingly, the lower motor neuron, the one that talks to the muscle, it actually always wants to fire off. It always wants to fire off. And the upper motor neuron, its job isn't to tell it to fire off, it's to tell it not to fire off, right? And so that's an interesting point, which has a clinical aspect, because there's something called upper motor neurons disease and lower motor neurons disease, and people who have spinal cord injuries. And depending on if they damage the upper motor neuron or lower motor neuron, they've got different clinical symptoms. So for example, if the lower motor neuron's always wanting to fire off and the upper motor neuron stops it, if you have an upper motor neuron injury, the lower motor neuron's always firing off at the muscle and the muscle contracts and you get spasticity. So people with an upper motor neuron damage, or who have upper motor neuron damage, tend to have spasticity in the corresponding muscles. But if you have a lower motor neuron injury, the muscle won't contract.
Yeah.
Right? And so then the muscle doesn't work at all. And so you have flaccidity, which is the opposite. So that just sort of, and so clinicians can actually look at somebody with a spinal cord injury and they'll know the level and position of the spinal cord injury simply from that, they get a good idea simply from that manifestation.
Wow.
Yeah.
That's super cool.
Yeah. So it is a real...
Yeah, well...
You haven't helped me at all. Because now I'll go back to, oh shit, maybe it's central nervous system.
Well, the one thing out of personal experience and a lot of the intracellular, extracellular, potassium, calcium, magnesium, all of that I can conceptually understand, but from personal experience, when I get cramps, either I'm deconditioned, I'm not as fit, I'm dehydrated, or I haven't fueled. So those 3 things, if I try and run a marathon, decondition, I haven't run in 6 months, try and run a marathon, guarantee I'll cramp. If I haven't hydrated, guarantee I'll cramp. If I haven't fueled with the correct, probably for me at that particular time, carbohydrates, I will probably get a cramp. So if I can cover those bases, be conditioned, be hydrated, be fueled, there's much less chance of me cramping.
Which tells me it's a metabolite issue at the muscle tissue. Because, again, some ion disturbance the utilization of fuel in the area, and all of that has to do with telling that muscle whether it can and can't contract. All of those things, all of them.
And the muscle, some type of muscle degradation at the time, because I guarantee I'm not going to cramp in the first half of the marathon, but I might start cramping with the last 6Ks or 5Ks to go. So whatever's happened, what type of damage I've done to my muscle is having an impact, whether it's a mixture of muscle damage at the same time, constriction, maybe an upper constriction somewhere, I'm getting tight somewhere, or something else is firing.
So I think it's all roads lead to Rome, and I think Rome is ion disturbances.
Yeah.
I truly think it's something's going on with either potassium, magnesium, sodium, chloride, or a combination of them in whatever way.
Yeah.
And it could be too many on the outside, could be too many on the inside.
Yeah, which is why just loading up on those things is not going to be the solution.
Exactly.
Yeah, that's crazy. Well, what? Oh man, there's too much of that now. Now my brain. Because now, what about other metabolic waste that could contribute to cramping, like things like ammonia and the lactate itself we talked about.
I reckon it could.
Ammonia, especially with a link in with the GABAergic systems. Oh, now we're going to have to do a separate podcast on cramps now.
Yeah. Well, we can try and dive deep and see if we can come to some conclusions. I don't think we will, but we'll try.
We'll find some questions, if nothing else.
Well, look, we've been going for an hour and 17 minutes, so guys, we're going to wrap this up, but I had such a blast listening to you talk.
Thanks for having me.
Thank you so much for coming in.
Good fun.
Yeah, we had such a good time, and I think we're going to have to probably do some more. I think.
I'd love to. And so it's the Dr. Mike and Dr. Matt show.
Yeah, so we've got a YouTube channel called Dr. Matt and Dr. Mike. We've got a podcast by the same name, so we're very unimaginative. And you can contact me on social media, Instagram, Twitter, TikTok. I'm at Dr. Mike Todorovic.
Yeah, but everyone follow the videos. They are brilliant. You get your whiteboard lessons. It's
all on the whiteboard, old school.
It's honestly the best thing ever. If you're semi-interested in learning about how all these things work and the intricacies of all of this, it is explained in layman's terms so you'll understand, or someone like me can understand and go, I've learned something today. And it's just epic. So guys, if you can, go follow along and enjoy, and we're definitely going to have Dr. Mike back on to talk about some more stuff. So thanks for coming in.
Thanks, boys.
Cheers. Thank you.